Yes, yes.
Okay. Now then, let's start with our second lecture, antenna design for aerial vehicles. First of all, I want to give you a short summary of our last lecture or of my last talk. And now I try to move the slides. I try to explain you very shortly which types of aircraft carries antennas. You can see it's passenger aircraft, military aircraft, so-called drones for military purposes, but drones also for civilian purposes. Then helicopters for military and civilian applications. And this was a look in history where, let's say, the first special or high frequency antennas were developed for instance, radar purposes. Here in this slide, you can see a lot of radio systems with the necessary antennas around the bottom and the top part of an airframe. Then I try to explain how an antenna works, or in other words, what is an antenna. And this was, let's say, our going in the antenna theory. And we have on the left side, in principle, a transmission line with a generator which excites or which can excite the antenna over the transmission line. Let's say in a very primitive picture, you can say the transmission line goes out in a conus, and this you can say it's in principle an antenna, or it works as an antenna. And the same on the receive side, completely the same, except the generator and receiver. And in the room between, it's the so-called free space with a special material behavior or a special material constant. Namely, this is our wave impedance. This is the 120 p ohm wave impedance. This is a special sign or a special constant, a special property of the so-called free space. Free space means in our case, it's not empty, not completely empty from any physical things. And this is also given here. Sorry. To scroll it with the mouse. Yeah, this is given later in a picture later on, in a slide later on, which is the square root of the material constants. It's the permeability and the permittivity in free space. And this is the reason of this value of 100 p ohm. I will change my pointer. To laser pointer, okay, it's a little bit better for discussion. And the reason, the necessary conditions for radiation was shown here. Let's say the core element of these radiation is at least that we have a change in time of, let's say, a current flow. For instance, a DC current flow makes no radiation, but in the moment, if we break it, this is a very strong change in time. If we break it, or if we connect it, means we have no current flow, and then we connect the two wires, and then current flow exists. It jumps up to a certain value. This both are time changing in current flow. This causes a radiation. Also, another possibility of exciting radiation on a wire is if we bend the wire has let's say constant current flow, and if we in a very short time bend the wire 90 degree or another angle, means it's a time change in direction of current flow, then we also cause a radiation. And yeah, this is let's say the standard case. We have a wire, and through the wire is flowing, for instance, a sinusoidal current, and then the time change is given by the waveform of the current. In all the other cases I explained, we have, let's say, a DC current, but the time change is coming by break, by connection, and by changing the direction. Okay, this is the main point from which we can excite or realize radiation from a wire. This was an example how we can imagine from a single resonance circuit was only coming from a charged capacitor. The capacitor is charged but not connected to the coil, not connected to this inductance. Otherwise, it's not possible to charge it because this is a short circuit for the capacitor. First, the capacitor is charged, then it's connected. In the moment it's connected, we have oscillation with going down magnitude. But in the moment we can bend the two plates of the capacitor in this way, then we also can realize an antenna which for a short time radiates here because of the capacitance and inductance realized. Yeah, you know the formula for such oscillation, and this frequency is in this moment radiated coming from the resonance conditions of this circuit. And here we only have to bend both parts of the capacitors as or it looks like a dipole. This is a very primitive example. It's only for understanding. In practice, it's not so easy to handle, because if you make the capacitance or you bend the two plates in this way, you reduce dramatically the capacitance, and also this oscillation changes very strongly in frequency range, and it radiates, but the frequency of radiation, it's not constant. This is all as a, let's say, auxiliary explanation out of the protocol. Here you can see the incoming or radiated field of a dipole in this direction here, and you can see that the E field components are in the direction of the dipole or dipole itself, and you can explain it either by the incoming field or by exciting a field by a generator with an inner resistance of R, like here, or this also can be, let's say, the resistance of a receiver input. Yeah, this is only another perspective of this radiation, what we can see. In the near field, we have some, in the first, if we make a snapshot, not closed lines, but in a certain distance of the dipole, we have closed field lines. Yeah, this was the explanation of the field components in the near field. It's the so-called reactive near field region. Then we have a, let's say, a between region with a high part of imaginary energy, but also a certain amount of let's say, real energy. It radiates outside. This is the so-called Fresnel region. And out of this region is the so-called Fraunhofer region or far field. Then if the antenna fulfills this condition here, means the distance from the antenna is much larger than 2 times the square of the let's say, the outer dimension of the antenna. It's the maximum dimension what you can find between 2 metallic points of the antenna divided by the wavelengths. This condition must be fulfilled, and so we have the so-called Fraunhofer region or far field. And all what we discuss now is based on this far field condition. Otherwise, it doesn't. It has not or is not valid. This is another look at this problem of field distribution in the near of the, for instance, the dish antenna, and then in the Fresnel region. This is here, this area. You can see the pattern or a little bit more detectable. And here this we can measure in a large distance from the antenna, means in the far field of Fraunhofer region. And especially in the case of, for instance, such a dish antenna, which you know, let's say, as a receiving system or receiving antenna for satellite signals for TV reception, then it's clear that if this dimension, let's say it's about 1 meter, then the distance for measuring the far field, it's not only a half meter regarding the wavelength of, for instance, 3 centimeter, it's 10 gigahertz, or 30 millimeters, it's 10 gigahertz. In most cases, we have frequencies higher than 10 gigahertz. It's only for explanation, only as a numerical example. Then we have distance from several 10 meters to realize only to measure the pattern of the antenna in this way. Yeah, this was our more or less last slide. We has to go a little bit in mathematics based on the Maxwell equations, and we can, in this way, we can explain a little bit better, or let's say in more detail, what happens in the far field. And at least we can see that the electrical field coming or radiated by a very small dipole. This dipole, it's named Hertzian dipole. It's very short.
Dr. Blau.
Yeah.
Sorry, could you accept another our group mates?
Yes.
Thank you.
Wait. Two guys waiting in the lobby, yes? Okay. I thought you are now a participant, yes?
Yes.
Okay. Then I proceed. Again, we can here see in the formulas that the field components in the far field depends not only on the distance r, the small r, as a, let's say, in spherical coordinates as a distance from the origin, and it's depends also on the angle of observation in both directions. For instance, this is the angle theta coming from the z-axis going down to the xy plane. This is the upper hemisphere. And then we also an angle in spherical coordinates, the angle phi. It goes around the x-y plane. And it's only roughly visible here in this point. This is our observation point. Then we can see that in the theta direction, this is this part here, we have a E-field component. And in, for instance, in R direction, this is here ER, in the R direction means in the direction of propagation. We also have an E-field component, but this is very, very small. And the larger the distance from the region, the more we can see this component as not existent or negligible. Again, you see the dipole, it's directed exactly in the z-axis. And this means in all planes which cuts the z-axis, we have this theta directed E-field component here, and perpendicular means in the phi direction we have no E-field, but we have a H-field, and this is visible here. This is this part. Means at each field point we have two components. One component is the E-field component. In the normal case, it's, let's say, the most important component. And but perpendicular to this component, we have the H-field component. Both components, the E-field component and the H-field component, it's visible here, are, let's say, coupled over the so-called wave impedance of the free space. Again, and this is shown here, I remarked it already. You can see here it's a square root of these two constants. It's the permeability in free space and permittivity in free space. And both components lead at least to the value, it's not written here, of 120 p ohm. This is the value of this quotient in square root. Okay, now here's the next one. And now we are proceed with this knowledge. This I have already explained in the first lecture. Again, this is only another schematic coming from the formulas here, from these two formulas, which is a part of the near field. And this is the gray part, and the white part, it's more or less identical with the far field behavior. It's only this, you can see here only this part of the formula which is coupled with the distance r. Here we have it in square, and here it's linear. Then this is the difference in the formula. And then you can see here it's crossing at the point 1. The far field region from wires, I wanted to go to, let's say, to the behavior of a dipole or of its, let's say, radiation pattern. Every antenna radiates electromagnetic field, and at least we want to know how the field is distributed in the free space, or better, what can we do to give the antenna a special characteristic. That means we want to illuminate the free space after a certain with a certain shape. It's the same if you have a lamp, for instance, and you want to illuminate a very small, let's say, circular area with a high brightness. then you need a special reflector, you need a special power of this lamp, and so on and so on. And similar problems we have also in designing, and this is our topic, is our problem designing an antenna. But first of all, we have to understand what happens principle regarding or based on the radiating mechanism. As I mentioned already in the far field, the terms in r or square and higher or cubic can be neglected. And this leads or not leads, this is given in a distance from the origin of our antenna, which fulfills this condition, means this radius of the observation point is much larger than the wavelengths. If we have a large wavelength, means a very low frequency, then it's clear we have to consider very large distances. Again, this formula, or let's say the basic formulas in free space, again, this is the E theta component, and perpendicular to this component, the H phi component, and the other components we can assume as not existence or zero. From a mathematical point of view, they are not zero. As I told you, it's only an assumption which makes the work for us a little bit easier. And you can say, okay, the E field, H field, in connection with the, let's say, a distance vector, or form a right-handed set, and fields are all zero at this angle, theta at 0, and P, I can explain you again why, and it reaches a maximum at half P. This is given in the XY plane. Let's switch back. You can see here, this is our dipole, this is the direction, and if you go with our observation point with a sensor or a measurement antenna, we can go to this point in the zenith, then we will see we have no field. We have a zero, a very deep zero, no field in this Z direction, either an E field nor a magnetic part of the field. And if we move our observation point or our sensor along this path, and we come here in this plane, in the XY plane, then we can find here a maximum. And this is very simple, visible on the functions here, on this sine functions. If this is the angle here, theta, it's 0, then we also have here 0. And then we have, in case of 90 degree or half P, then we have 1. This is the maximum. It's very simple with on hand on this mathematical expression. Okay, the wavefronts are actually spherical, but a small section of the wavefronts is indistinguishable from a plane wave. If we observed, let's say, the radiation of the antenna sufficiently far from the antenna, it's clear. If we go very, very far away, then, and we only look in a small part of the surface of the sphere, then we can assume that this plane we are discussing and we want to measure the radiation behavior in this area, we can accept it as or imagine as a plane wave, but only in this very large distance. Otherwise, it's not fulfilled. And now we want to we want at least to discuss this problem, the radiation pattern. Yeah, how can we realize, or how can we explain, or how we can we measure a radiation pattern of an antenna if we if we do not think about all the problems? We can say, okay, let's use the antenna. The antenna is mounted on a mast or on a tower, and then we can take a drone with a sensor. Means it's a very small receiver, and this receiver can deliver the measured field strength values or incoming power, can deliver it, detect it, and can make a record in a memory. You can imagine this. And so we could fly again here. So we could fly with a drone around our dipole, and we can make from our measurement results snapshots from a lot of points. And if we have the coordinates from all these points around the antenna, then we can make, let's say, we can realize a grid. This is what you have seen here. Imagine we have all measured these points where the lines are crossing here. It's clear it's several hundreds or several thousands measurement points, and in this way we can determine the radiation behavior of a dipole. But in case of a dipole, this is a very large effort what we have to do, and so we can do it a little bit easier by thinking about what happens regarding the field distribution based on mathematical expressions. If we want to plot the power radiated from an antenna per, now we have here this special word, unit solid angle, or its radiation intensity, U, then we only can multiply the power density at a given distance with the square of the distance. And I try to explain this a little bit more. This is a general expression of what is written here. This is the so-called radiation intensity. You can use the letter U or another one. We have used here the capital U. And this is our distance, let's say our measurement distance from the origin, or in square, and this is the power density. Power density, the word says what happens. We had to use a power at this point divided by the area. In our case, if we feed in the antenna the power P, then this 4πr square, this is the surface of a sphere with this radius r. And so it's very simple. The radiation intensity is given then by this, again, this expression. If I multiply these two parts here, then we only have the power delivered to the antenna, or better going out, not delivered, going out of the antenna. This is better because we will see later there's a little, or could be a little difference because of efficiency and so on. Let's say this is the power going out from the antenna and divided by 4p. This quotient is the radiation intensity. Now you can say, I can do nothing with this expression. For what is this good, or how it helps us? And now let's look to the Hertzian dipole. We want to know the radiation pattern of the Hertzian dipole. And then we look to the time average Poynting vector. Poynting vector is the real energy going out from the origin, from our antenna, from the feed point to a certain point in free space. This is given by a half product of E theta and H. This is the conjugate complex constant of the magnetic field. H phi, we know we only have these two field components, and we can substitute the HV by the expression of the electrical field strength divided by the wave impedance. We will see it in this next formula, and or this is the radius standard vector. Now the radiation intensity can be expressed by this. We hold the same expressions, 4 square multiplied by, look here, and now we have substitute this both are vectors, and E theta multiplied by H conjugate complex, you know, it's a real value at least. This is shown here. And we have here substitute H by E theta divided by wave impedance. So we have a very simple expression. And then we have to insert for the E theta, the magnitude of E theta in square, the expression we already have developed or already have known and is visible here in this simple formula. You will see later on, as long we are discussing about wire antennas, we can very often use this and these expressions. Yeah, and then we are coming to this expression, and it's not necessary to know the current, what is driven into the region in the antenna, means in the Hertzian dipole. It's not necessary to know exactly the length of the dipole. The length is very, very small, but it's not zero. So, and why it's not necessary, and here, this is our sine function, this is necessary. Over this function, we have to develop the cut of our, let's say, set y or set x plane. We'll see it in the next slide. Means the radiation pattern we can realize, or we can see by normalizing our radiation intensity u by x maximum value and plotting the result. Okay, how we can come to the maximum? Very simple. We look to all these things. The k, okay, this is 2p divided by lambda. Current in the origin, the length of the dipole, it's in both cases the same. The only thing is the sine function here, sine in square. Yeah, the sine in square can only deliver a maximum if the angle of theta is half p or 90 degrees, and this is the maximum of this expression. Yeah, and so we can write the formula in this way here. This part, it's open divided by the maximum, means the sine square function, it's 1. Then we only have this sine in square function. This is the radiation pattern in a special way, in a cut, because you have to imagine all this radiation intensity, it's only valid, let's say, as a parameter of phi. And this is visible here. You can see here we have it's a cut in rectangular way. If we make the cut, which we can see from this formula here, then this is the area of the cut. This we can see then. But here we, for a better understanding, we had make a cut not completely through this toroid-like figure. We make a cut here along the x and along the y-axis, and the direction of the planes we have to look, it's the z direction. Our dipole, again, it's located here in this direction. Means if we look from this side to the dipole or from this side to the dipole, we cannot find any radiation. And if we go from this angle, let's say theta is 0, to values of higher than 0 degree, then we can see when we came here in this plane, in the xy plane, then we have the maximum of radiation. The same is in the This is the upper hemisphere, and the same is in the lower hemisphere. It's the same, exactly the same behavior. And because it's normalized to the maximum, then we can also write here on the y-axis or on the x-axis here for the magnitude 1. And in this way, it's not necessary to fly with a drone around the Hertzian dipole. We can determine this diagram on this, let's say, more or less very simple way. And this is again written here. The field intensity along a direction theta and phi is given by the length of the position vector to a point on the surface of the 3D shape in the direction of theta and phi. In every slide you also can find the source of literature. Yeah, and if we look again, let's say to this figure, this is this I have explained, and now we make a cut in perpendicular direction, means we make a cut in the XY plane through this toroid, through this figure. In the middle here, the diameter is 0. Yeah, it's a, let's say it's a toroid with an inner diameter of 0. It's at least only the diameter of the dipole, but yeah, it also goes to 0. And if we make a cut in this plane, and then we can see this behavior, this diagram means if we fly around the antenna, around the dipole, it's directed from our eyes through the slide. And then we can see here that we have a constant radiation distribution around our dipole. And from this point of view, we can in principle use also a dipole, a small dipole or a half wavelength dipole. I will explain it later. We can use this type of antenna, we say, as a gain standard. If we can guarantee that our antenna, means in this case dipole, has a good match. What does it mean, a good match? I will explain later. Means the power coming from a generator, it's delivered to a dipole, and this power, it's more or less completely accepted by the dipole. Means the delivered power goes completely in the dipole, and so the dipole has a very good power matching value, and so the power delivered from the generator goes in the dipole and goes from the dipole in the free space. This is what I want to say with a good matching. And if we have a good design dipole, we can use this dipole as a, I mentioned it already, as a gain standard. Means if we want to determine the behavior or the properties of another antenna, what we have designed, but we didn't know exactly how the antenna works and so on, then we can use the antenna in brackets dipole, our gain standard. We can use it also for measurement purposes, because the well-known gain value of this dipole, it's very precise to determine, and so we are able to realize measurement results with a dipole as a gain standard. You will understand it in more detail later, because we come also in the last part of this lesson to possibilities how to measure an antenna. What can we do with the measured or with the determined radiation pattern? This is a question, and you can see here only a more or less primitive example of such an antenna. It's not a dipole, it's clear, it's another antenna. Why it's not a dipole? Because we can see here that our, let's say, main part, main pattern, is much smaller than that what we have seen in the slides before. And it's also asymmetric in this cut plane, this cutting plane. And then we see the antenna must have, let's say, a higher concentration of field energy in, we say then in this direction, it's the main direction. You can see the antenna delivers the radiation only in a very small angle. And this part out of this, the energy is not zero, but it's very small. And here it goes more or less to very small values. And you can see here one of the main parameters what we can find out from the radiation pattern measured or determined by simulation or by mathematical formulation and calculation by hand or with a PC. It's the half power beamwidth. This is this angle. 3 dB means this is in logarithmic scale, means it's the half power. Here we can measure the full power, and the angle between the half power points means 3 dB points, exactly minus 3 dB. Yeah, not only 3 dB minus, it's, if this is the maximum, is for instance related to itself, maximum divided by maximum means normalized to the maximum. It's 1 here, the value it's 1. In log scale it's 0, and then if you go down to the half, then we have minus 3 dB. You know the or I hope you know the definition of this decibel discussion or measurement or determination. It's given by 10 times the logarithm for base 1 for the basis of 10 times the logarithm of the decade logarithm of the relation between a measurement value divided by a reference value. If we make a normalization of a maximum, it's clear what is given. In every case, the quotient must be out of any dimension. If there is a dimension, meter, square meter, millimeter, or whatever, then it's wrong. The quotient must be without any dimension. It must be dimensionless. And then you can apply this decadic logarithm multiplied by 10. The multiplication by 10 is coming from, let's say, practical purposes, because the engineers 20, 30 years ago want to save, to look to the pocket calculator, and so this factor of 10 spreads the parts after the 0.132, and then you shift the comma one part to the right side, and so it's easier to calculate it in your head. Yeah, this is the decade logarithm. And then we have another parameter. It's the so-called front-back ratio. It's also very primitive. If we here have 0 dB, because it's the maximum in logarithmic scale, then we only look to this value here. All the values must be in log scale, is clear. And then this value is, you can read out directly as front-back ratio, it's clear. And also the values, the maximum here, the maxima here and here, or then let's say the so-called side lobes, the maximum of the side lobe suppression or side lobe level. And it's clear, if you want to design a good antenna, then with high gain, then you want to have that the half power beam is very small, and additionally you want to have that you have low side lobes, and that the back lobe is also as small as possible. Then, in other words, what do you want? You want to radiate all the power delivered to the antenna to a certain direction from the antenna in the free space. This is at least the purpose of your antenna. In practice, in the meantime, we have a very large variety of antenna systems and with special features. And later on, you will see that it's not only the main purpose to use an antenna which radiates the input power to a certain point in the free space. Then you also will find that also the antenna has, let's say, we say zeros here, or here zeros. This is specially designed because you want to suppress some distortions coming from a certain point from the free space and goes to your antenna. Means you want to suppress external signals which are not wished to receive. The antenna is the first, let's say, schematic element in a receiver or in a transmitter, which allows you, in this case, to suppress, let's say, not only signals coming in a certain frequency range, also to suppress signal coming from a certain location. Sorry, I have to make a break for 1 minute, wait. Sorry, thank you for waiting. Let's proceed. Again, the antenna is one of the first elements, or let's say schematic elements in the front area of a receiver or transmitter, which allows to suppress unwanted signals coming from a certain angle from the space, out of the space. This is not possible with the receiver itself. It's only possible with the antenna. Here you can see a 3D, a full 3D diagram of such an antenna. It's in principle, yeah, it's not the same like here, but it's a little bit complicated. And we also have cut through special cuts in the antenna, let's say, measurement philosophy. We have normally, yeah, this is a practice. If you want to buy an antenna, you only get diagrams in 2 special cuts. The first cut is, and it depends how the antenna is located for receiving or transmitting purposes. It's either elevation or either the azimuth. And this is a normal, regarding this diagram, a cut in the Y-Z plane. The x-axis is perpendicular to this plane, or the other cut, it's made in the x-y plane, so the z-axis is perpendicular to this plane. And this is visible here. On the left diagram, you can see the radiation pattern of this antenna. Let's switch back. In this case, this is the ZY plane. We can here see the very large half power beam width in the ZY plane. And then the next diagram, this is the XY plane cut, because in this area means in the XY plane we have very small half power beamwidth in opposite to this one here. It means the antenna, it's not an extremely high gain antenna, but it's a high gain antenna, what we can see here. And again, here you can see that in every case, the maximum is 0, means in this case here, we show at least always the, we say directivity, not the gain. We say only it's the directivity. Directivity means it's the pattern of the antenna related to a certain reference value, in the most cases, of the highest gain point or of the highest gain value, so that from the diagram or the radiation pattern itself, you cannot determine the gain value of an antenna. What does it mean? I will explain you with the next slides. The only thing is here that you understand what happens here, and this is also written here. We have the YZ cut visible here, and here we have the XY cut. This is the cut with, let's say, the higher gain, not the higher gain, sorry, with the lower half power beamwidth. Yeah, and the term, if you speak about elevation or if you speak about azimuth, depends on, let's say, the mounting situation of an antenna. Yeah, we can explain the directivity. Again, means what we can here read out of this pattern. We can determine the directivity by, for instance, the radiation intensity of antenna in a certain direction. We can see this angle in either in theta direction or in phi direction, and this is related to the either mean radiation intensity in all directions. It's the mean value, but we also can use the maximum. And this mean radiation intensity in all directions, you can substitute by radiation intensity of isotropic antenna radiating the same total power. Means is a isotropic radiator which is consuming the same power like the antenna we have to determine regarding the directivity. But again, you can also use, and this is the same, you can also use, instead of this, let's say, general explanation, mean radiation intensity in all directions, you can also relate your directivity on on the maximum of radiated power, and it has the same function, and you will get the same results. Now we have seen the 3D diagram or the pattern of the Hertzian dipole, and now we want to know what is now the directivity, or at least the gain. But here the directivity, it's given in dBi, means in our case there's no difference between directivity and gain. I explain later why. The directivity, it's normally only the behavior of the antenna related to a value of its rotation diagram, means maximum, or here this, or radiation intensity, or this. And if you look to the Hertzian dipole, we can see that the directivity can be shown to be with this value 1.5, or if in logarithmic scale you can achieve, or you can calculate this value, 1.76 dBi. This small I means it's related to the isotropic radiator, means to spherical radiation behavior. And now we can explain it a little bit in more detail. This is our next topic: radiation resistance and efficiency. Let's start with the efficiency. What is the efficiency of an antenna? The antenna, or every antenna, consists of metallic parts, maybe strips, maybe aluminum parts, maybe copper parts, maybe wires or massive metallic parts, then a reflector made from aluminum, made from copper, and so on. And all these parts has a limited conductivity. In a lot of, for instance, simulation programs, you have a perfect electrical conductor. This assumes that the conductivity is infinity. And in our case, or in practice, we never have such a perfect conductor which has a conductivity of infinity. It's impossible. And so it's clear that we have in every case losses inside the antenna, because this is in principle, or was one of our first topics, how an antenna radiates, and the base point was a current flow. We need a current flow, and if a current flows along a non-perfect conductor, then it's clear that we have a voltage difference at the starting point and at the end point of this wire where the current flows. And this, it's clear, consumes power, heats up the wire. Maybe it's very small, very small. It's maybe not measurable, but at least it's the case that we have a power dissipation in, let's say, the power is dissipated in as thermal power. And this is not wished, it's clear, and we can reduce it to a very low value, but not to zero. And because it's not to zero, then we have to speak about the efficiency. This, let's say, small letter E, means nothing else than the power radiated in a free space, divided by the power delivered to the antenna, means to the input ports, input terminals of the antenna. And we can express this very simple with the so-called radiating resistance. In the slides coming now, we have to discuss what is the radiation resistance divided by the radiation resistance plus our loss resistance. And you can see this here, radiation resistance or and loss resistance or loss. And if you look in the antenna, we find this radiation resistance. This is only an equivalent schematic. It's not visible on the antenna itself. It's only equivalent schematic. How can we explain the behavior between these two terminals? We measure here, we apply a voltage, measure a current, and now the measurement system shows us a certain impedance. And impedance consists of a real part. This is the sum of these both. By the measurement system, we cannot decide, or we cannot determine what is the radiation resistance and what is the loss resistance. It's impossible, because we only can measure the impedance together. And here maybe there is an imaginary part, can be equivalent to a capacitor or can be a small inductance. It's open. We measure here inside, and then we determine only the impedance. And this is shown in more detail here. here the same antenna terminals. And now let's look in our generator itself, which excites the antenna at the antenna terminals. The inner resistance or the inner impedance of an sinusoidal generator, which delivers, for instance, 100 megahertz, it's an example, can consist also of a real part of the inner resistance and also an imaginary part. To realize, let's say, matching, I mentioned it at the beginning of our lecture, then we have to try to achieve the so-called conjugate complex matching. Means because all the elements which you can see here are in series, means that these two imaginary parts should be in opposite. For instance, if you have here capacitive like imaginary part, then this should be an inductive like part, so that both parts also from the, let's say, from the value, from the magnitude, can compensate each other. Then this minus J plus J, it's 0. And in this case, we also speak about resonance. It's the case for a resonance circuit. And in this resonance circuit has no imaginary part, has only real parts because of the losses we already discussed. Yeah, and if we can achieve this, then the antenna is together with our inner resistance of the resonator, it's in resonance. But in practice, you will find normally generators with this X source. It's very, very small, means it's negligible. Yeah, in practice, we have only a generator with, for instance, a 50 ohm system, and it delivers the power to these antenna terminals. And to achieve a very good power matching means that no power comes back from the antenna, it's not reflected. Then we have normally to insert here special matching networks, which compensates, for instance, this value of X, the imaginary part of the antenna. Here are some basic formulas. If the antenna is resonant, means it's compensated by an additional element, then means this imaginary part is 0, it's clear, it doesn't exist. It's in case of resonance. Then the source impedance, it's clear, there's nothing else than what you can see here from the antenna, looks inside the generator. Then you can see this, both elements as an impedance. And if you look from the generator side in the terminals of the antenna, then you can see this value, this impedance. And the antenna is, or better, the source is matched to the antenna, means the power which the generator can deliver goes completely in the antenna. And under this condition, we have to fulfill that the source impedance is the conjugate complex value of the antenna impedance. And this is the case not only if both values are compensated, additional, we have to ensure that also the real parts must be the same. And this is given here in this condition. Then only for looking in the future, this is, you can express this behavior by a so-called reflection coefficient. It's we say it's a rho, and this is the relation between two voltage wave components. Voltage received by voltage incident. You can, in case of wave theory, this has the dimensions of a power. It's in a lot of cases it's handled like a voltage, as shown here, and you can express this with these two relations, with the difference of your antenna impedance minus, and in practice we have here, for instance, 50 ohm, and the same here. We have here the impedance of the antenna, and here we insert the source impedance with 50 ohm. Means this ZS is in practice measurement technique. It's normally a real value. It's not an imaginary part. It's not an impedance. It's insert, or it's used namely by 50 ohm. And so the so-called reflection coefficient, if this is let's say a complex value, this also is a complex value, means also the result is a complex value. But the reference value set S is a real value, and this makes the problem of reflection coefficient a little bit easier to handle. This is only an explanation. It's not typical for the next slides. It's only, let's say, a look in the future regarding the measurement of the antenna impedance. As you know, it's very important regarding to determine again the efficiency of an antenna, to find out the relation between radiation resistance and the sum of radiation resistance plus loss resistance, and then together with what our generator delivers to the antenna, means if we can ensure that the delivered power from the generator goes completely in the antenna, or it's a part of it, it's reflected back. What is now the radiation resistance and efficiency? Okay, efficiency we have explained. The radiation resistance itself is explained, or let me explain it, based on the formulas we have developed with the Hertzian dipole. We go out from, for instance, an average power density as we know it already, and this is defined by, you remember the S from the Poynting vector, directed power going the free space. This is the real part of the quotient, and here this field conjugate complex value of the E theta value divided by the wave impedance, it's in principle the substitute of the H field. If you see this quotient here, it's the substitute of the H field. Poynting vector, it's the cross product of both components of H and E field, and this is visible here, but not only the cross product of this complex values, it's the real part, because we only look to radiated power as a real power. In imaginary power, it's not transmitted in free space. It's maybe you can, let's say, explain it around the antenna in the near field, but it has nothing to do with radiation in the far field. And we know the expressions regarding, in case of Hertzian dipole, we know the expressions in the formula before. You find it here again. This how is theta, eta. This is our wave impedance. I use this value here because in the literature they are pendling, depends on the books, either with Z0 as a wave impedance 120 p ohm, or this value it's absolutely the same. If you see it, you can substitute it by Z0. Okay, now this is our normal, the radius vector, the value of the radius vector in all direction. It's normally 1. And here we know these values K, the current delivered in the origin of the dipole, the length of the dipole in square. And also it's well known from our developed formula. We have the sine square of theta, of the angle theta, divided by the square of the radius or observation distance. Yeah, now how we can realize, or how we can explain or develop the radiation resistance. The radiated power we can obtain by integrating the power density, again, power density over the sphere radius. Yeah, that means it's clear we want to know the power which goes through the surface of this sphere at yeah, it's determined by the radius also of our observation point. And now this is given with this formula. The integration part, it's for one angle 2p 360 degree, and this it's only for the upper hemisphere because it's the same like the lower hemisphere. And you can see here our power density, then the radius vector, and these two angles we have to integrate it. The theta and phi means azimuth, around the azimuth, and a part regarding the elevation, the upper hemisphere. Yeah, and if we carry out the integration, this is the formula. We insert the values here, what we have developed with our Hertzian dipole. You can see here is the wave impedance divided by 2. Is this part? Then also this K. K, it's 2p divided by lambda multiplied by the current at the origin multiplied by the length of the dipole. Dipole is very small, but it's not 0. And here divided by 8p. And this is now discussed by, or this is developed by the integration here. And now if you integrate it, you can find this as a result. Means the radiated power, it's the wave impedance multiplied by p divided by 12. Then the current and the origin in square, and also the relation between the length of the dipole to lambda. This lambda again comes from the K here, also in square. And now we look to a definition of the radiation resistance. And this, it's given in this formula. It's very primitive. The radiated power we can express by a half, and the current at the origin in square, this is nothing else than the Ohmic law, and this is what we want to know. This is our radiation resistance. The half comes because we have to use the average for power, and the current we have to insert the maximum values. If we excite this is important to mention. If we excite the dipole with sinusoidal waveform, sinusoidal voltage, this is the peak value what we have to insert, and this is if you have to peak by peak and want to know the average power, then it's the half. It's 1. The mean value here, the mean value regarding the maximum, it's 1 divided by the square root of 2. And if we have here the square, then 1 divided by square root of 2 in square is a half. This is the explanation for this factor 1 divided by 2. Yeah, this is a very primitive expression coming from our ohmic law, and what we can do is this is equal to this developed radiated power. Yeah, and if we set this formula equal and we look to the expressions on both sides, then we find that we have a radiation resistance in case of a Hertzian dipole of 20 p in square, and with this expression, length of the dipole divided by lambda in square in ohm. Yeah, and here I can show you the exact value. All the time I said this is what we have discussed. It's coming from the Hertzian dipole, but in the literature you can find here two different values. This is the value here coming from the theory of a constant current distribution along this very small dipole, all the time named as Hertzian dipole. But here this is another approach coming from two very close together arranged point charges. Yes, if you have not a small wire, you have only two point charges very close together. Then from the theoretical point of view, you also can calculate this as a so-called radiation resistance of a Hertzian dipole. But it's not a wire, it's again two very close together arranged charges. And this it's valid, let's say, for a wire like Hertzian dipole, very, very small, not zero. And yeah, you can see both expressions or differ by a factor of 4. But okay, this is literature, but it's not a problem to think about, because in practice you never can realize a Hertzian dipole. It's only, let's say, for explanation. But what we can do is we can try to build very small dipoles, not in the near of zero, but with a length much smaller than the wavelengths. And then we will see that we, with our results, we came very close to values or to results which is applicable in practice. And here I have already shown what happens if the relation between the length of the dipole to the wavelength is much smaller. It's clear then our radiation resistance must also be very, very small, goes in principle to zero. It's not zero, but goes to zero. And if we increase the length of the dipole, it's only for understanding, the relation should be about 1, means the length of the dipole, it's not no more a Hertzian dipole, it's a full wavelength dipole. And if we insert only the values here in this formula here, then we find out it's about 200 ohm. But it's only a fictive value. It's not realistic in practice. But it's, let's say, in the near of a useful value. Maybe in practice it's 70 or 75 ohms or whatever. Means we have also a quotient between these two values of 3, for instance. But it's not the same if you have, for instance, here a value of 200 and on the other side of 2. This quotient should be too much. Okay, only for warning, you cannot only use the formula what we have developed for a Hertzian dipole or in the near of a Hertzian dipole. You can insert let's say a length of the dipole of its 1 wavelength. Why? Remember, all the time, and this I will be shown in the next slides, all the time we discussed about not in the focus, but the current distribution. This is let's say the main point. The current distribution of the Hertzian dipole is assumed to be constant. And this is the base of all these discussions, and it's the base of all these developed formulas. In the moment, if the current distribution is not constant, then you cannot apply all the formulas what I have shown you. And this will be explained later on. And next, and this is what I already said, the next interesting parameter of an antenna is the so-called power gain. And the power gain is the ratio of radiation intensity to that of an isotropic antenna radiating the same total power. Yeah, this is very important. And the directivity and the power gain only related by this very primitive formula means the gain is nothing else than the directivity multiplied by the efficiency. If the efficiency is very high, means the losses, the inner losses of the antenna, because it's, let's say, full metallic, then the losses are very, very small, not zero, but then the efficiency, or this value E, is in the near of 0.95, 0.99, and so on. And then we can say the power gain, it's nearly the directivity. Yeah, what we have here, this is another look to an antenna, but regarding or in connection with the power delivered to the antenna and to say, let's say, a consumer, a person who wants to apply the antenna together with the generator, and in a certain frequency range, what is allowed to use. I give you an example, for instance, the Wi-Fi or WLAN system, which has a frequency range of, let's say, about between 2.5 and 2.6 or 7 gigahertz, or between 5.6, 5.9 gigahertz, depends on the country and the standards. And in this area, for instance, it's allowed to radiate. Yeah, and this it's printed on a label for Wi-Fi 20 dB milliwatt, and this is called EIRP. 20 dBm EIRP. What does it mean? Yeah, the logarithmic scale 20 dBm means in a linear scale 100 milliwatt, and now it's shrinked to 100 milliwatt EIRP. What does it mean? If I have let's say a Wi-Fi output generator, or let's say a PCB which delivers 100 milliwatt, means 20 dBm in log scale, then I have to give it, or I have to connect it with an antenna, and the antenna has a gain, let's say, of 6 dB, 6 dBe, no, sorry, 6 dBi, means the antenna has a gain in linear scale four times the gain related to isotropic radiator, means to a radiator which has a pattern like a sphere. And this is here visible on the left side. This is our sphere with, in this case, with the radiation intensity. And the antenna has a gain of 4 regarding the behavior of the sphere. So if I deliver now the 100 milliwatt to an antenna, which has a gain of 4 in linear scale, means the antenna radiates in the free space 4 times 100 milliwatt, not in all directions, but only in this direction. In this direction, she delivers a power of 400 milliwatt. And this is not allowed because on the label it's printed the power, the allowed power, it's 20 dBn means 100 milliwatt. EIRP means we have to consider the gain of the antenna, because in this case, if we deliver 400 milliwatt, this would mean, or this could be allowed if on the label were printed 20 dBm plus in log scale plus 6 dB means the allowed power EIRP is 26 dBm, but it's not allowed because it's printed 20 dBm. So what does it mean? We have to consider the gain of the antenna, and so we have to make the opposite. Means nobody knows in which direction the antenna radiates, and this measure, or this let's say figure of merit, or this value here, EIRP, means we imagine that the antenna is possible to radiate in every direction of the free space, because the antenna has a 6 dB gain, mean has a, it's not identical with a isotropic radiator, but we don't know in which direction the antenna can radiate, and so we have to assume the antenna acts like isotropic radiator, because she can deliver the energy in this direction, this or this direction, and this is yeah, let's say only a safety measure, a safety figure of merit. And so we have to make the opposite. If it's printed 20 dBm, EIRP means we have to consider the gain of the antenna, and in log scale we have to calculate the EIRP minus the gain of the antenna. Or we can look at here in the linear scale, the EIRP is the product of the allowed power and the gain of the antenna, or in other words, the allowed power which you can deliver to the antenna. It's the quotient of the EIRP and the gain of the antenna here. And in log scale, it's a difference. It's clear. You have log of the given EIRP minus the gain of the antenna, because it's in the denominator. So this is what I want to explain regarding the equivalent isotropically radiated power. This yeah, value, or this measure you find in a very large number of equipment which can radiate electromagnetic waves outside or in the free space. Normally this is in this case a problem of distortion, means not regarding of health problems. In this case it's a problem of a distortion. But I know from our students in Germany, if to bridge the distance to the access point with a high reliability, they also used antennas with gain of 10 dBi or so, and yeah, it's clear then you have a better signal to noise ratio or signal to noise behavior. But on the other hand, you can distort you can distort other consumers, other participants of they also looking to the same access point, because the antenna acts as a receiving antenna and also as a transmit antenna, means radiates from your PC power in the environment, in the free space. And this is the problem, not the receiving power. If you only can switch the antenna, let's say as a receiving antenna in this case, then it's allowed. Then you can use an antenna with a high gain or with a much higher gain, but you have to ensure that the antenna with this high gain never can act as a transmit antenna. And this is the problem, and this is not so easy to realize in practice. Yeah, here again, some pattern, and now you can here find first this term azimuthal pattern and elevation pattern. Yes, and this depends on the installation of the antenna. Normally, the azimuth means the antenna it's arranged in such a way or localized in such a way that she is equivalent with the let's say with the horizon. And if you look from your observation point to the horizon, then you look in this direction of the, or in the azimuth. And elevation means this is the angle from the horizon. Perpendicular means in the direction of the sky. If you look to a car and you want to know the elevation pattern, means you want to know the pattern of the antenna from the street plane in direction of sky, or in case of azimuthal pattern, you mean the direction in around the car. You can imagine here in the middle is the car, and now you look around the car, or in other words, you turn the car around, and here, for instance, here or here, you have a measurement system, and you can measure the behavior of the antenna inside the car, which delivers, let's say, a constant output power, and then the car is turned 360 degrees, and then you have this pattern. This is a very good pattern because the so-called forward-back ratio is very good, and yeah, means all signals coming from here, let's say from behind, are suppressed very good. And if you look to the scaling here, this is 0 dB. The antenna has in this case a gain of about 8 dB or 8 dBi, I have to say. Don't forget the I, because it's related to isotropic radiator. And then if you look here, yeah, this is this circle means about minus 30 or minus 40 dB. It means it's very good. It has a very high suppression of signals coming from behind. And I guess this is the elevation pattern, means the pattern in this. If I make a cut here in this plane, then I will see this one. And if this is a car, for instance, you can imagine it's not so easy if you want to measure this elevation pattern to turn the car, let's say, around this axis. It means you have to use a very large machine to put up the car and turn it around the axis, going, let's say, through the doors of a car. This is not so easy. And in this case, we also use, in case of elevation pattern, we also use the upper hemisphere and not the lower hemisphere, because in case of a car, it's clear the car is moving on ground and only looks in the sky. In our case, means in case of aerial vehicles, this is another situation. We have in most cases not to look in the sky. In a lot of cases, or in most cases, we look down to ground, because the other part of communication, the other side, receiving or transmit side, is localized on ground and not on a satellite. Also, a satellite is flying much higher than an aircraft or an aerial vehicle. But again, in most cases, the communication goes between aircraft and ground station. Yeah, then we have some other interesting figures of merit. I cannot say, let's say, measures which characterizes an antenna. First of all, a very important parameter is the bandwidth, and this is often defined as the frequency range over which the power gain is maintained to 3 dB, but this is very old. You know, 3 dB, it's again a loss of the half power. And now we in modern measurement systems, in let's say in practice, in a lot of papers, you will find that the bandwidth is determined by the return loss, or by in logarithmic scale, it's the magnitude of S11. S11 means also the input reflection coefficient, what I have shown you before, related to 50 ohm in log scale. This is a return loss, and this return loss, let's say the value, the limit which determines the bandwidth, it's this 10 dB. If I say return loss, then I give the value 10 dB. If I go to the scattering parameters, it's the same. It's only another expression. Then we have here minus 10 dB. It's only a question of the relation. Okay, and in voltage standing wave ratio, it's this value. It corresponds to 10 dB, and it's not greater than 2. Yeah, the bandwidth is given by voltage standing wave ratio not greater than this value 2. Yeah, what is reciprocity? Reciprocity, it's the behavior of the antenna, because the antenna, it's a linear device. This you have to keep in mind. Antennas are normally absolute linear devices. So far they are built from metallic parts, PCB and so on. Means all the parts are normally passive things, only driven by outer power or outer voltage source, creating a current, and so on and so on. And under these conditions, we can say an antenna is a reciprocal device. Why? And here I try to explain you what is reciprocity. Let's assume we have here a dipole named antenna A, driven by a voltage source V, A for antenna A. Voltage source A here in the middle, sinusoidal, this source drives this dipole. And now we have a second dipole as a receiving antenna. And this dipole should have more or less the same dimensions like this one. It's not necessary that this dipole has a special, let's say, a special localization regarding to this dipole. You can choose any distance, you can choose any location of the dipole of this second antenna B to the first antenna. Doesn't matter. The only thing what you have to what you have to ensure is that this localization, it's hold constant. in this second arrangement here. The arrangement means the localization of both antennas are hold constant for both cases here. Case 1, this antenna A is excited by the voltage of antenna A, and now it's clear the voltage drives the antenna A, and then a current is created along the strips or wires of antenna A, and energy is radiated. High frequency energy is radiated to the antenna B, and the antenna B receives the energy and creates along the wires a special current, and this current, it's named current B. And this current B, and if both antennas reciproc, the current B has also to flow. If we exchange now the situation, means we use for antenna B the same voltage source what we have here used for antenna A. It's now the antenna. It's now the antenna B, or voltage source of the antenna B. And now we measure the current here of antenna A. And the measurement of the antenna A must be the same like in case of the antenna B in the first situation. And if this is the case, then we can say both antennas are reciprocal to each other. If we have hold the situation, the measurement situation, localization of antenna A and localization of antenna B, like here, then we will see we have exactly the same current in antenna A regarding this in relation to antenna B. Okay, this is the definition of reciprocity. Yeah, let's go to the next slide. We discuss now about effective antenna departure, and what does it mean? If an antenna is used to receive a wave with a power density S, we already know what this means. It's the power per special area, for instance in square meters. It will produce a power in its terminating impedance of PR, let's say receiving power in watts, and a constant of proportionality between the received power and the power density is, for instance, this effective antenna aperture, this AE, the effective aperture of the antenna. And we can express this with the received power, for instance, is the effective antenna aperture or effective antenna area multiplied by the power density. It's clear. If we have a given power density in a free space and the antenna has a special effective area, effective aperture, then we can very quickly calculate the received power. And then in the next step, we discuss about the gain, means how strong the antenna can concentrate the received electromagnetic field to, for instance, small receiving angle or a small half power beam width. Then this is, for instance, related to in this formula, the antenna gain. It's, for instance, the 4p divided by the square of the wavelengths multiplied by this effective aperture of the antenna. Yeah, and if we use this approach, then we can go to we can develop the so-called freeze formula. What happens with an antenna in free space, either as a receive antenna or as a transmit antenna. And if we look to both antennas in opposite, let's say in place B, let's say in place A, we have a transmit antenna, and in place B, we have a receive antenna. Both antennas have, for instance, different gains. Gain of antenna A, like here, TA, and then we have an antenna B, for instance, here with a gain B. Yeah, what happens with the transmission between such two antennas? We know that the power density depends on the surface of a sphere. If our wavefront moves spherical outside, then at each situation we can make a snapshot and we will see our wavefront it looks like a sphere if we look to the observation point. And if we go more and more far away from the origin of our antenna, then the surface of the sphere will be larger, larger, and larger. Means the power density in a certain area, if we hold the area constant, the power density will drop down, will be smaller, smaller, and smaller. And this is in principle given here. And also we have only, let's say, a restricted transmit power. We cannot increase our power to megawatts or larger values. We are limited on the Earth with all things, and also with transmit power. There are a lot of reasons or why we have to have such a limitation. One reason is maybe the battery capacity or let's say the availability of a power plant or whatever. And then we have other restrictions which limits the transmit power. Depends on technical things, depends on the losses, the diameter of wires, and whatever. What I want to say is we have a lot of restrictions, not only coming from the generator, also coming from other things, and also things of health, of health, that we cannot exceed a certain power level in a certain distance of such an antenna. Okay, now the receive power, it's given if we apply this formula here with transmit power multiplied by the gain of the antenna A. It's the transmit antenna. Then we have our effective aperture of the antenna. This is the receive antenna B. And here we notice this is the surface of our sphere, this value here. And this determines at least our receive power. Yeah, and then if we use the quotient between receive power and transmit power, yeah, then we have a very, let's say, similar formula, because in this case, the effective aperture of both antennas is substituted, and then we have the product of both gains. And here we have, in principle, the surface of a sphere related to the wavelengths. And this gives us, at least the so-called transmission behavior between 2 points with an antenna gain A and an antenna gain B. Yeah, here this determines the distance between the two antennas, and then we can very simple calculate what happens if we have two isotropic radiators. Means every antenna radiates in all direction with the same intensity. Then we can here insert 1 as gain. It's valid for isotropic radiator. And then you have here, let's say, the free space losses between 2 points, a point A and a point B. And the distance is here given by R. This is the so-called Friis formula for transmission losses in free space between two antennas or 2 points. Very simple, and yeah, it's only coming from the theory of wave transmission or wave radiation based on the behavior of the wavefront in spherical coordinate system. Now let's start with the last point in our lecture. This is the so-called polarization. I already mentioned that if you have a dipole, the E field vector, it's moving in a certain direction. For this purpose, let's switch back to this diagram in spherical coordinates. This one, I already told you that if the dipole is localized in direction of the z-axis, then the E field vector, it's moving in this direction here, yes? And this has nothing to do with, let's say, with the E field itself, that here in this point, the E field goes to 0. This has to do with the, let's say, with the observation point, because in this case, we are looking only to the axis of the dipole. And the dipole in this case has no extension, so there is no current flow, it's clear. If we go to this point or to other points, then it's nothing else than the, let's say, another angle of observation, so that the extension of the dipole will be longer and longer. And here at this point, we have the longest extension to this dipole. The dipole is very short, but it's not 0. But if we look at this point to the dipole, it's clear, then we can see nothing, because there's no length where a current is flowing and where a current can radiate anything. And only in this plane we can observe an electromagnetic field or a component of the E field in this direction. And perpendicular means here in phi direction, we can observe or measure also the magnetic component of this electromagnetic wave. And additional means in this direction here, in the phi direction, we cannot measure, from theoretical point of view, we cannot measure no E field component. Yeah, and here it's again explained here. The E field component in the phi direction here, perpendicular, or in other words, in the XY plane, it's 0. This is only from theoretical point of view. In practice, if you have an antenna, not an Hertzian dipole, an antenna, let's say, half wavelengths or 1 wavelength dipole or whatever, or monopole, then we can observe that we also have in this normally not existent plane a very small value of the electromagnetic wave, I mean in the E field. We also can determine in this plane a very small E field component, not only in this plane, also in this plane. And later on we will see that this distortion in this direction makes, for instance, from a linear polarization, which is given in theory in this plane. It's a exactly linear polarized wave because only in this direction we have an E-field component. And then in practice, we have let's say a distortion in this plane, in this perpendicular area, where only a H-field exists. Then we can say, the polarization is not exactly linear. Then we speak about, for instance, elliptical polarization. I only mention it so that if you hear it, you can sort it, can qualify it. Let's go back to the polarization. The polarization direction, it's, as I mentioned, given by the direction of the E-field vector. And the polarization state of plane wave could be expressed in terms of the relative amplitudes or magnitudes of the orthogonal components of the electric field. And this is given here. This is the complex value of the of the E-field component. It's the magnitude, the pure magnitude, and here in the brackets you have the components. And it's clear in this moment when I make in brackets have two different components, then it's clear that we have not only one component in one direction. Then we have E theta. This is our normal component, and this is the unit vector of this E theta direction. And then here, normally it's 0. Then we have an E phi component, and this is the vector perpendicular to this vector. And we can write this formula now in this wave, in this way. This is our magnitude of the E field, and this is the polarization vector. Yeah, what is given in the brackets here, it's now this way very similar described. Yeah, we come to the last minutes. In other words, it was already mentioned from my side. If you look to these values here, these are special values. For instance, if you have a component of the E field in the feed direction or in the depends on the direction of rotating, then we can see, if we look only to the components, has nothing to do with magnitude, like here. It has only to do with direction of rotation. Then we can explain this. I will do it later in detail for right-hand circular polarization or for left-hand circular polarization. It's only given only with this angle normalized or normalization vectors. Because we have the power of 1, both components are given in peak values. And then if you look to the power, it's clear if you square it, then the peak value, it's 1 divided, the mean value, not peak value. Mean value is defined by 1 divided by square root of 2 in both cases. And if we combine it to look for the total power, then we have here 1 divided by square root of 2 in square. It's then again the half power. What it's contained in this wave. And my last remark is, look to this very simple sketch. You see the motion of the electromagnetic wave in this Z direction. It's, let's say, described by the Poynting vector, is direction of propagation. And we have here the two components. This is the E0, it's only the magnitude. The components are, for instance, EX and EZ, it's not shown here, but it's expressed here with the H field in the Y direction, HY. But regarding to that, what I have explained, you have in parallel to each Y also and EY, a very small component. And yeah, you can see it here or here. This is the general description of the E field vector in this direction, and the same in for the H field in this direction. And now the E field vector, you can compose it of X and Y linearly polarized plane waves, and this is what I have explained. Here you have the normalized vector in X direction and here in Y direction, and means at least exactly the E field vector is not only moving in this plane, it has also small components in the perpendicular plane. Okay, now this is the end of our lecture, and the next lecture is in next Tuesday, same time. Thank you for your attention, and if you want or if you have questions, please you can formulate a question and let's say send it to me over over a colleague who can collect the questions, and then I will try to answer the questions at the beginning of the next lecture. Thank you again and have a nice evening.